A very important type of algorithm is the one called divide and conquer algorithms. And as the name suggests, these types of algorithms work by dividing the problem into multiple instances of the same problem, but with smaller sizes, and then solving them, and then you combine the results. So binary search is a typical example because, well, you make the range of your search narrower and narrower at each iteration until it becomes just a single element, in which case searching becomes trivial. Okay, and many divide and conquer algorithms are recursive. This is a typical case because the definition actually hints this, that you divide the problem into multiple instances of the same problem. Since it's the same problem, you apply the same algorithm to solve the smaller problem. Okay, the smaller size, that is the key. So you divide your large problem into a number of smaller problems, but to those smaller problems, you apply the same idea. It's the same approach. So that gives you a recursive function. Here's an example, a very typical example for recursive functions. Compute the factorial of a number, an integer that is greater than or equal to 0. Of course, you can do this in an iterative manner, which we call the non-recursive way, or we can also do it in a recursive way. So let's see how we can do this. And obviously, in the iterative way, you just multiply the numbers starting from a 1 or 2 up to n. That's it. So you initialize the value you are going to return to 1, and then you multiply it by 2, and then 3, and then 4, etc., up to n, your input number, whose factorial you are going to compute. And when the loop is done, you just return the product. That's it. So this is the iterative way. And let's look at the recursive way. And this obviously is based on the famous observation that n factorial is equal to n times n minus 1 factorial. Now, I named this function factorial 2 to indicate that it's a different function from this one, okay? And that function appears here, factorial 2. So that is the recursive version. And what happens here is, you see, this is the actually basis case. Obviously, if f is less than or equal to 1, which means it's either, sorry, this should be n. If the input is either 0 or 1, then you should just return 1, because that is the factorial of 0 or 1, in which case you do not need to do any computation. Or you have some number input that is greater than 1, in which case you use this relationship. You return n times the factorial of n minus 1. Because I have this function that computes factorials, I can use it to compute the factorial of n minus 1. And then when I have that value, I multiply it with n to obtain the final result. In fact, you can actually follow the execution of this algorithm. Like, for instance, if you would like to compute 4 factorial, you would put in factorial 2, the name of the function, 4. So 4 is going to be the input value. And then the first thing you do is compare your input 4 to 1. But this inequality doesn't hold. Therefore, I do not return 1. I go to this case. I need to return n times factorial 2 n minus 1. And n in this case is 4. So I need to return 4 times factorial 2 of 3, 4 minus 1. So now I need this value. And then I apply 3 to my function again. And it's not less than or equal to 1. So I come here And to obtain that, I need to find 3 times, which is n, factorial 2 of n minus 1, which is true, which is 2. So this becomes 4 times 3 times f2 of 2. And then when you apply the input 2, again, it will not go into this if clause, and you'll come to here. Therefore, you will have to return 2 times factorial of 1. And then factorial of 1 will be executed. But since now my input satisfies this inequality, then I'm going to return a 1, and 1 will be replaced here, and then you can multiply these to obtain the final result. But that is done internally. You don't need to do it in your function definition. So that is the elementary difference between iterative functions and recursive functions. Now, as we already studied recursion in the context of mathematical induction, and we talked about recursion in that context, we have an idea about what recursion means. But here, I'm going to give you 2 examples of recursive sort algorithms. The first one is the merge sort. And what this does is, you essentially have a sequence of numbers, again specified here, a1 through an. Okay, so you actually separate this sequence into 2. Okay, and then you sort these within themselves. Okay, 2 of them, and then you combine them together. So for instance, if your sequence is 2, 5, 1, 4, you divide this into 2, and then you merge sort these 2 subsequences, 2, 5, and 1, 4. Now, essentially, what you do is you again split it in half. You have 2 by itself, 5 by itself, and you also split this 1 by itself, 4 by itself. And now you see my merge sort function returns the first value, which is the only value, if n is 1. Look, n is the number of values in the sequence, which means if your sequence consists of just a single value, you don't need to do anything. You just return as is. Otherwise, you again separate the list into half from n over 2. So a1 to am, m indicating the middle, and list number 2, am plus 1 up to an. So the merge sort actually sorts these 2 separately, as it sorts 2, 5 separately and 1, 4 separately. And then you combine them together. So when these are applied to merge sort, they are going to be returned by themselves. So you are going to need to merge them. So how do you merge them? That is the key. The heart of merge sort is the merge procedure. Separating the list into 2 is not that difficult. The actual work in merge sort is in the merge function. I'm not indicating the details here, okay, but essentially what you do is you compare these 2, and you decide that 2 should go before 5. So I have now merged the 2, okay, and then if you merge, I'm going to merge 1 and 4 together. Again, they will be 1, 4, because that is the correct order. And then I'm going to merge these 2. To be able to do that, you look at the first positions that have not been merged yet. So 1 and 2. 1 is smaller, so I write it somewhere here. Okay, so this is gone. And the first unmerged value here is 2, and here it's 4. So compare 2 and 4. 2 is smaller, so it has to go here, and this has been merged. And then what is remaining is 4 and 5. So 4 is smaller, So 4 should go here, and finally 5 should be here. So that is how merge sort works. And the important thing about merge sort is you need to be careful about when implementing the merge procedure.